Welcome at Eindhoven University of Technology. Normally our campus here behind me is crowded with 15,000 students, particularly in springtime like this. Unfortunately, due to COVID-19, it's empty now and we can't meet here together in person. At Eindhoven University of Technology, we develop knowledge related to the issue matter of digital concrete. Sometimes in isolation, in case of fundamental research, but mostly in close collaboration with the industry. Eventually, all this knowledge should find its way to the industry to accommodate an architectural degree of freedom in design, sustainability, and a higher construction productivity. Today, we're going to visit the housing project here in Eindhoven, Project Milestone.
We are here in Eindhoven, in the city district Meerhoven-Boswijk, and we are here on the construction site of the first 5 digital concrete houses. And people are really gonna live in these houses. We started cooperation with the 5 parties. The Technical University of Eindhoven, Eindhoven Municipality, Witteveen en Bos, that's the engineering of the house, Weber BMX, they are gonna print the house, and Van Wijnen, we are the building manager and we're gonna build the house. We had different meetings about the building, the structure and the design of the house. And it's very special that we now have the permit to build the first 3D concrete printed house. The design of the houses is made by Hubbe van Mierlo Architecten. There are big stones, menhirs from Asterix and Obelix, and they are landed in this field. We are using a parametric model and we made the design of the house in it, and also it's the structure of the house. So we can send it to the robot and we can print with it. For this project, we don't use a steel wire in the concrete element. We have a special design of our house and we made a structure that we don't need a steel wire. Let me explain the structure of our house. We're first making the piles in the ground. That's the first part of the foundation. And after that, we are making the slabs in the concrete print factory of Weber BMX. And that slab, that's for transportation of the wall elements and also the second part of the foundation. On that slabs, we're going to print the wall elements. And after that, we transport them to the building location and we put them on the piles. On the wall elements, we put a wooden rooftop, and on the wooden rooftop, we put the parapets. And it's also from printed concrete. For the first house, we use a rooftop from wooden beams. It's actually a traditional way of building. For the next houses, we want to use a prefabricated wooden floor, or maybe we print the floors and we put some reinforcement in it. Weber BMX is going to print 5 houses.
Welcome in our print factory that we own together with BAM and Weber BMX. Here we will print the houses for the project Milestone. Before we started printing, we had to solve quite a few challenges. One of them being the cantilever of the outside wall, the second one being the long printing time, up to 16 hours for producing the element. The third being the permitting. This place has to be safe because people will live in it. And of course the last one, logistics have to be solved as well. The answer to solving the challenges is having a robust system. Robust with regard to the printing system, so the mixing, the pumping, the robot, but also a robust system regarding the mortar. With regard to the mortar, we have decided in our product development to stay with ordinary Portland cement as the binder. The drawback of an OPC system is that you have to find a way of being able to stack layers on layers without the bottom layer giving way when you put on a next layer on top. This problem has been solved to make sure that we have modified the rheology so that we get thixotropic characteristics in our mortar. But another benefit of having an OPC mortar is that the rules that apply to concrete, you can extrapolate this to this mortar because a lot of things are known about ordinary concrete. Another thing is when you have a mortar that doesn't harden immediately but that has an open time of about 90 minutes, it's much more easier to get a monolithic structure. That means that the quality of the layer of the interface, that's the layer between the layers, has the same performance as the bulk of the material. That is extremely important when you have load-bearing structures and when you need the permitting that we need for this house. And it's even worse when you have layers adjacent to each other, so not on top, but next to each other. There we have to guarantee as well that the quality of the interface between layers is of the same nature as the bulk of the material. And with this product and with the system we have, we can guarantee that this is obtained. We have a robust mortar, but also we need a robust system. So for the system, we have an silo mesh pump from MTech and SMP. We did modify the system a little bit. We changed the water dosing in order to have a more constant quality of the mortar that is being mixed and pumped. And we swapped the rotor stator in order to have a smaller amount being pumped as is being required by the robot. We have an ABB robot on a track, and we have the possibility to print with a round nozzle and with a rectangular nozzle. The drawback of the rectangular nozzle is when you have a print pad that has curves, you will have to make sure that your nozzle follows the curve, and therefore you need another axis of your robot, reducing the reach of your robot. Then we also have an inline quality measurement system to make sure that we guarantee and control the quality of the end product. This sensor that is inline measures the yield of the pump, the viscosity of the mortar, the density of the mortar, and the pressure that is being applied by the pump. From the yield of the sensor, we have a feedback to the frequency controller of the pump, guaranteeing that we always pump the same amount of mortar. This makes sure that the layers, when we put adjacent layers next to each other, they are the width as we want them to have, so we have a monolithic character of the interface of the material in between the layers. Then from the viscosity measurements, we have a feedback to the water dosing, helping us in guaranteeing a constant aesthetic appearance of the element that we print. Then of course the pressure sensor is just as an extra quality control issue if we have a problem with the pressure, that the system shuts down and that the whole system does not explode, so to say. One of the other issues we had to solve was, let's say, the logistics, and for this purpose we print on a slab with anchors that we can hoist, so we don't have to hoist from the printed material, we hoist from the concrete that has been casted on a truck and from the truck to the building site. Well, with all these measures we have changed from a proof of concept to a technical readiness level of about 7 to 8. But still, of course, there is room for improvement and making things better. For more details, please see the paper in the conference proceedings, and I would love to see you in 2021 when the house is finished on site.
When this house is ready, we're gonna take the learnings from this first house to develop the next houses. So that's smarter detailing, using a better printer technology, and also use smarter processes to build this house and develop this house. The aim for the last house is to print the house really on this location. For digital concrete printing, we foresee development to use reinforcement in the concrete, but also using less material in the concrete and have a sustainable mortar for the future. We have a question for you, academic world. Is it possible to develop a method or a way to print with different kind of materials, so that we can print reinforcement in the concrete, or maybe print a tube for electricity or for water? Is that possible? Thank you for this innovation and good luck with the next steps.